multiply this, 30, that would be 120, that would be 360. Oh, that's even easier maybe. Okay, C, 10 factorial. Okay, now we're getting pretty, but we could do some things. So that's 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. We could throw some things together. Here's our 10 and 10 make 100, right? And then we could put some other things together, but probably want to go with a calculator on this one. Or if you have a factorial key, which I think every scientific calculator, as well as if you have a scientific calculator, you don't have a graphing, you should be able to find a key that has this on there. And you could do that. And what does it turn out to be? Well, this was 6, this was 720, and this is what? 3,628,800. Okay. So, D says how many zeros does 3 factorial end in? None. How many zeros does 6 factorial end in? And then the question is why? And then how many zeros does this one end in? 2, and the answer is why. Can somebody tell me why this one has no zeros, this one has 1 0, and this one has 2 zeros in it?
If it ends in a 0, it has to be a multiple of 5. And since the 3 factorial has no factors, doesn't have 5 as a factor, it won't be 2.
Okay, in order to get a 0 on the end, it has to be a multiple of 10, right? But 10 is a multiple of 5 and 2. And I've got a 2 here, but I don't have a 5. Right? Let's take a look here. I've got 1 0. Where did it come from? Well, the zeros come from being a multiple of 10. 10 comes from 2 and 5. I got my 5 here. Did I get my 2 from here? Well, maybe. But there's also 2 2s there and a 2 and a 3 there. So I could have put the 5 with that 2 to get it. Or the 5 with that 2. Or the 5 with that. It doesn't have to be that 2. Right? But how many 10s can we get? Just 1. Because I only have 1 5, no matter, even though I have 4 2s. 1, 2, 3, 4 2s that I could use. Because a 10 requires a 2 and a 5. Does that make sense? So when we get to here, I got 2 zeros on the end. Where did they come from?
The 2 times 5.
This 5 with a 2. Well, which 2? I've got 1, 2, 3, 4, 5, 6, 7, 8 2s. Now, in fact, we know that this number, because of what I just did, 1, 2, 3, 4, 5, 6, 7, 8, we know that 2 to the 8th is a factor of that number. Does everybody see how I got it? Pull it out of there. What is 2 to the 8th? 256. 256 is a factor of this number because we know that. However, how many 5s have we got?
2.
This one, and that one. So, can everybody see that 2 seems to be very abundant, but 5 is more scarce than the 2? So really the thing that's going to limit us on this is not our 2s, but our 5s. If we can figure out how many factors of 5 there are in the number, that'll tell us how many zeros to put on the end. Can everybody follow that? Because for every 5 I have, I'll have plenty of 2s. So, where do the 5s come from? Where would the factors of 5 come from? Well, let's say I go up to 15 factorial. That means I'm going to have a 15 times a 10 times a 5, and I haven't filled in the 14, 13, these other numbers like we did all of these. But I really don't care about them. How come? Why are they not important anymore?
They don't have the 5s.
None of them have the only ones that are going to have 5s in them are the multiples of 5, right? So, the question we ask, how many zeros does 10,000 factorial have? That means I've got 10,000 times 9,999 times that. But every fifth number will have a factor of 5 in it, correct? How many of those numbers are there? How could we find that out?
Divided by 5.
Divide what by 5?
10,000.
Divide 10,000 by 5. And what do we get?
2,000.
We get, there are 2,000 multiples of 5.
I have a question. But like some numbers, they can end in a 0, they're multiplied together. Like, oh, they're all factors of 5 and 10.
5 and 2 to produce a 10.
Yeah. Okay, never mind. I just figured it out.
Okay? Does everybody see that there will be, in this big old list of numbers that start out 10,000 times 9999 times 9998 times 9997 times 9996 times 9995. That one is going to have a factor of 5 in it. And that one's going to have a factor of 5. And every fifth one as we go, for a total of 2,000 of them. Each one of those, I could pull the 5 out, put it with the abundant 2's to produce a 10. So is the answer 2,000? Why not? Because as I start listing the multiples of 5, these are the list of 2,000 right here, right? I'm starting on it. When I get to this number, what happens? I'm going to get 2 5s out of there. How come? Because 5 times 5 is 25. So instead of getting just 2,000, I'm going to get some more. But how many of these kinds of things will there be that has more than 1 5 in them?
Every power of 5.
What do you mean every power of 5?
Like 5 to the... Like
5 to the first
then 5 to the
will
second.
produce these 2,000. Right? Then if there's 5 to the second, which is what number?
25.
25, that will produce 2 factors of 5. In other words, I'm looking for all the multiples of 25.
Oh.
What are they? Well, this is the first one. What's the next one? 50. Then what's the next one? 75. How many of those are there? How many multiples of 25? Because for every multiple of 25, I'm going to get 2 5s. You follow what we're saying?
You can divide 2,000 by 25.
Divide what?
2,000. Or, sorry, 10,000 by 25.
10,000 by 25.
Yeah.
What do we get? That's pretty easy to do. 400. So if I took 1 times 25, I'd get my first multiple. 2 times 25, I'd get 50. 3 times 25, 75. 4 times 25 is 100. When I went my last time, 400 times 25, I'd get 10,000. So there are 400 of the numbers that will, having already produced one 5, being a multiple of 5, are going to produce a second 5 because they're a 5 squared, and there are 2 5s in there. And so I've already counted one of them when I did the multiples of 5.
Yeah.
But I didn't count the other one, so I need 400 more. Is that everything? 2,400?
What about 5 cubed?
What is 5 cubed? 125. So how many 5s when I get my number to these numbers to 125, how many factors of 5 will I pull out of that?
3.
3 of them. Well, I've already got 1 when I did the multiples of 5, and isn't 125 also a multiple of 25? So I've pulled a second one out of there, but I haven't pulled the third one. Does that make sense? So I'm going to have 125, and then what's the next one? 250, 375, then what? 500, then 625, and so on. We'll just 750, and those how many multiples of 125 are there?
80.
Well, we take this and divide it by 125, and that will be 80 of those. Does everybody see what we're doing? Now what?
5.
Are there any 5 to the 4ths? What is that number? 625. Yes, there are. How many? Well, all we've got to do is take that number and divide it by 625, right? When we divide this number by 625, what do you get?
16.
How many?
16.
16? Point something? Or is it going evenly? Even. Okay, so there are 16, and let's take a look. Of course there are, because those 4 5s went together with some 4 other 2s, right? And made the 4 10s that made this up. So it does go in 16. All right? When are we going to stop? When do you stop? Let's just check the next one. What's 5 to the 5th? Well, it's this times 5. What's that?
3,125.
So when we got to 3,125, we will have taken this one out for the multiples of 5. This one out when we did the 400 multiples of 25. This one, we would have taken this one out when we did the multiples of 125, and this one out when we did 625, but by the time we get to this number, there'll still be one more 5 left, right? How many of these are there in there? Now we're going to get to a decimal number, and how many is it? 3.2, so the 0.2 doesn't count, right? Then what? 5 to the 6th? What's that?
15,625.
15,625. How many of those are in there? None. Because it's bigger than the number. So we don't need to take any more out. All we've got to do is add these up. Is that making sense?
Yeah.
That's kind of a tough problem, but I think you knew everything you needed to know. Just thinking about it in the right way to get it to work. Anybody want to ask a question on this problem before we leave?
Not on this specific, but with other numbers, so we're not always going to have 10,000, 20,000, something like that, but let's say we have 4,198. Do we always round down?
4,198.
Mm-hmm.
Factorial.
Factorial.
Okay.
And we're trying to find the trailing zeros.
You find how many trailing zeros? There would be some in there, right?
Mm-hmm.
Yeah. Not as many as
No.
here, because it's a smaller number.
And let's say we get a decimal like we did with the last one, do we always round down?
Yeah.
Okay.
Just take your whole number and, yep. So you find out how many 5s there are, multiples of 5, how many multiples of 5 squared, how many multiples of whatever,
I just thought it was interesting. When you're looking at the numbers, it goes 2,480. So 2 times 2 is 4. 4 times 4 is 8. 8 times 8 is 16. 16 times 16 is 32, which is 3.2. I just thought that was kind of interesting.
Okay. Powers of 2 with zeros or scientific notation shifting the decimal place somewhere to. Thank you for that observation.
Math is magic.
You what? It's got patterns in it, that's for sure. All kinds of patterns. Any more questions about this problem? Which other one do we need to talk about?
The house number.
The house number one?
Yeah.
Who was successful with this and could, Devin, do you want to come up and,
I don't know that I felt confident like teaching it, but I was able to work it out.
I'll just say this, I don't know that you have to feel confident for you to come up and have us help you. And I'll just say this, when you come up, the one who learns the most is usually the one coming up. So this is a learning opportunity, and it's going to be safe. Nobody's in here going, with these kinds of problems, nobody's going to make fun of anybody with, if you struggled with these. These were tough problems. If you did this all by yourself, without Googling anything, without talking to any neighbors, and you got every one of these completely right, yeah, maybe you should be teaching this class rather than taking it. But can we help you? Do you want to bring your work up to show, because that might be helpful. Is it on your computer?
It is not. I actually worked through it with my husband at
Oh,
home.
okay.
My husband's in calculus, so he's kind of...
All right. Do you want to come up and show us what your approach was and what you did? I'll get this other stuff out of the way.
Do you still have the... So, he has 3 children, and the product of their ages is 72. And then the son is their house number, and the census taker asked so that he still couldn't find out how old they are. My father said, "Oh, that's right, I forgot to tell you that the oldest one likes chocolate pudding." And obviously the fact that they like chocolate pudding is irrelevant.
Did you figure that out?
I was so confused.
But what was relevant is that he has an oldest. So the oldest one cannot be a twin. So you can't have, your largest number can't be a duplicate. You can't have 2.
Okay. So how did you start?
So if you factor this out into different numbers, and I just kind of played with it, because obviously if you can have 1 and 72, but that doesn't work because he's got to have 3 kids, and obviously.
But let's prime factor this, because we could use what I think this is a great idea. 1 and 72. 72 is not prime, and neither is 1, and we don't even want to put 1 in a prime factorization tree because that doesn't get us anywhere, right?
So obviously you don't have that.
So go ahead and let's prime factor it. What does make up 72? Go ahead. Choose 2 numbers. 9 and 8. Are they prime?
No.
Keep going then. So what is the prime factorization of 72? Everybody agree with her? Okay. Now how might that help us?
So this is how I ended up giving it, is this number, 2 times 2 times 2. 2 times 2 is 4, times 2 is 8. And then you have 3 and 3. So if you times this out, 8 times 3 times 3 equals 72. And he would have an oldest child.
That doesn't account for the fact that when she went to the door, looked on the house number, she came back and said, I still can't tell.
The ages?
Yeah.
So then it wouldn't be 8.
You have to keep in mind,
It'd be
it
closer
says
to
this was an elementary teacher who worked for the Census Bureau and not teaching. Every teacher moonlights a little bit somewhere, right? To try and make ends meet. How many teachers do you know that all they do is teach school? They don't do anything else. It's rare. And this was an elementary, so this is an elementary teacher. They're brilliant. They know. They walked out and said, I can't tell. Why did they say that?
When you find all the possible products that equal 72, there's and then you sum all of them, you add all the.
Do you have some?
Yeah.
Can we trade off? You've got us moving very, very nicely. Okay? Come up and show us what you came up with possibilities and.
Okay, so I did this too, but there's a whole bunch of things that could equal 72.
Leave that there. Let's erase over there and write over there. So show us some things that give us 72 from the 3 kids.
Okay, so some of the products, there was 1 times 1 times 72, but since it has to be children, that doesn't work. And then there was a 1
Poor mother. If you had kids age that, oh man.
1
Yeah.
times 2 times 36.
And that's not much better, but it is a little more feasible, right? A
And
mother
then
could do that.
times 3 times 24, also not a child. And then 1 times 4 times 18. And then when you add these, so then 1 plus 4 plus 18 is 23. And then we keep going, 1 times 6 times 12, 1 times
Can I stop you for just a second?
9.
Can anybody see an organization behind her approach? She's writing these down in a... She said, I'm going to take 1 and 1 and 72, and then she's keeping the 1 and saying, well, what's the next biggest number I could use for that second child? You follow that? She said 2, and then you have to find what the third child would have to be to make that 72. Notice how she's going up, raising that up as she goes. Why is that a great strategy?
But I can tell you, it's a good strategy, but right now you're at a point where it wouldn't work.
What do you mean
8
it wouldn't
and
work?
9.
She's not
You can tell
done.
the age difference between 1, 8, and 9.
Right, but just, okay, so then when you're summing these, this is 18, 19,
That's the sum?
19, yeah, and then this is 18. So these are the sums. And then you keep going, so then 2 times 18 is 22.
Now how do we know there's not any more that have 1 in them as of their age?
She's gone all the way up to the factor.
Because she went all the way up to these, using what Devin gave us over here of 2 cubed times 8, she's used a 2, a 3, a 4, that's 2 of those, right? A 6, that's one of these and one of those. An 8, right? That's all of those. What's the next thing she would move to? 9. Well, if it was 1, 9, then what would the other child have to be? 8, and that's the same kids, right? So there are no more with 1s. That's everything. So by doing it in an orderly way, she says, okay, and I'm going to start with having one of the kids be 2 and go from there. Why didn't she go 2, 1 something?
So it'd be the same as.
Because that would be the same as 1, 2 something. Because so it would be 2, 1, 36. Well, that's the same as 1, 2, 36. So she's avoiding those repeats. She doesn't need to use 1 anymore, so we won't go back there. Keep going.
Okay, so 2 times.
Give us your whole
2
list.
times 18, and then 2 times 3 times 12, 2 times 4 times 9, and then 2 times 6 times 6, or 3 times 3 times 8, and 3 times 4 times 6. And then the sums of all these, 2 times 3 times 12 is 17, 15, 14, 14, and 13. So the only ones that are repeated are these. And that's why she couldn't tell, is because there were 2 that were 14. But then he said the oldest.
And the house number was 14, and we know that now because that's the reason she couldn't tell. So then the hint about the chocolate pudding tells her the answer. Does that make sense? The reason she couldn't tell is because there were 2 that had the same sum. Had she gone out and looked and it says, oh, it's 19, she'd say, oh, your ages are 1, 6, and 12. If they'd said 18, it should say 1, 8, and 9. If it was 22, she knew all of those combinations and knew their sum. But when she went out and looked, and the answer was, the house number is 14, I can't tell because there's 2 possibilities for that. That's why she needed the last clue. Okay, did this have anything to do with number theory? What we've been studying? Whole bunches. In fact, you don't even need to pick your calculator up. Just as an example. If you know that, if you know the prime factorization, 3 2's and 2 9's, you can say the 9 is in here along with one of the 2's, and there's the other 2 2's. And then you say, well, what would be next? Well, it's going to be 2, 3 something. I'm going to move the 3 from the 18. That will leave what here? If I move a 3 here, I'll move a 3, but the 2 that was here, I'm going to move back over with that, and there was already a 2, so 2 times 2 times 3, that's where the 12. You can almost pull them apart and put them back together in all these different combinations by knowing the 2 cubed and the 3 squared. Because there's got to be, in all of these combinations, you've got to find that. There's 2 of the 2's, the other 2's over here with the 2 3's. There's a 2 and a 3, so the other 3 must be over here, and the 2 other 2's must be with it, and so on. So you can kind of double check that as you go. Okay? A little kind of a funny twist on number theory. Are those the 2 hardest? Yes? How about the other ones? Any of the other ones?
I have a hard time with the laundry one.
The laundry one. Who was successful? Do you want to share with us that? Thanks.
Which board do you want me on?
Sideboard's good.
Alright. Thank you. Alright, so basically I was just going through all of the multiples. We have 4, 5, 6, 7. Every time you try and made a stack, that was really fast work. Every time you try and made a stack with these guys, there's always 1 left over. So it didn't matter what you did, there was always 1 left over, and it went all the way through except for 7. And so I figured I had to find a multiple that went into all of these, but, hang on, okay. Alright, so I just started listing out all of the multiples. This is probably better. And so I tried to do, let's say, 20. I know 20 goes into these two, but I know it doesn't go into 6, so I know that doesn't work. I tried 30, and I knew that went into it, but it didn't go into that one. So I just started listing all the multiples until I got to all the way to 301. So 301 goes into 7, but 300 goes into these guys. So that's why there was always 1 left over. Because the multiple of 7 is how many, or 300, there were 301 sheets, but there was always 1 left over, because 4, 5, and 6 can only go up to 300.
So you just kept looking for multiples of those numbers, and then when you got to 7, there weren't any left over, and, okay?
And like, I kept looking at all of the factors, like for 17, I know 7 times 2 equals 14. And then it was 1 off from 3 times 5, which is 15. And I saw some correlation between all of those. And so I knew, like, for 4, 5 times 4 is 20. However, 7 times 3 is 21. So I just had to keep going until I found all the mismatched ones to where all of these have multiple, and then this one you just had to add 1.
Okay. Did anybody else have any other insights into this problem as you were doing it? Did you care to
I found
jump up there and show us what you did?
I got tired after a while doing these problems, listing each multiple, because it can get really long, so I went ahead and found the least common multiple of all 3 using the Wolf RAM Alpha.
Okay.
Which that's an awesome website. That helped me with my homework through and through last night. So the least common multiple that I came up with was 90, and I just did the least common multiple of 4, 5, and 6, because 7 was always going to be just going to have 1 extra. So the least common multiple of 4, 5, and 6 was 90. So I went ahead and looked at the multiples of 7. I did multiply those out because I couldn't figure out how to do it. And then one of the multiples of 7 is 91, which made me think if there's always going to be 1 extra for these, then 91 went in. So that's 91 sheet or 91 tablecloths or whatever it was, because it went into stacks of 7 evenly, because it was a multiple of 7. That was the least common one I found, but with your example, there are all multiples, but that was the least amount of tablecloths that I found. That
Question? Comment?
Isn't the least common multiple of 4, 5, and 6 60?
I don't think 4 goes into 90.
What? Yeah, 61 doesn't go into 70. So the least common multiple that would fit this equation.
Yeah, but 4 doesn't go into
Went to
90.
4 goes into 90, doesn't it?
Go into 92.
Oh, yeah.
2.5.
Oh, then maybe
Oh, yeah. Okay, it doesn't work. But I thought it did.
You used the idea of LCM, but you didn't get the right LCM.
Yeah.
So what is the right LCM?
60.
Oh,
60.
this is why. I told you the wrong numbers. Is 4 one of the numbers in the problem?
Yes.
Okay. I didn't do 4. I just did 5, 6, and 7. And so
Okay.
it works.
It works for this.
For these numbers.
Nice.
I missed that number. Sorry.
If you can't do the problem that I gave you, just change it. I'm just kidding. The LCM ideas could help us, yes.
Yeah, what I did was I took the paper that we did for the homework that one day, And I was thinking, well, if it's gonna have a remainder, like if each of them are gonna have a remainder of 1, well that means like 5, you know, is always gonna end in a 5 or a 0. So I thought, well, if there's supposed to be a remainder of 1 with 5, then it's gonna end in either a 1 or a 6, right?
Did you ever hear that?
Yeah.
Say that again.
So I was thinking about the multiples of these numbers, and I thought, well, to have a remainder of 1, when you're dividing by 5, it's always going to be a 1 or a 6. It's always, that number's always going to end in a 1 or a 6.
Does everybody agree with that? It's got to end in a 1 or a 6. Keep going.
So I just started going through this list, and anytime I found a number that ended in a 1 or a 6, I would divide it. Oh, at first I would divide it by 7 then, because then if it was divisible by 7, then it almost fits everything. Then I would see if it was divisible by 4 and 6, right? Because I would check with 5 and see if there was a remainder of 1, or I guess the number right before that. See if it was divisible by 4 and 6. Does that make sense?
Mm-hmm. Yep.
So
Good insight. Yes.
I did the same thing, but because I knew it had to end in a 1 or a 6. But then I went further with it, and I knew 4 would never go into something that ended with a 5. Does that make sense?
What do you mean in a 5?
Okay, so the number had to end in a 1 or a 6, so the number below that had to be divisible by all of them. Does that make sense? Because you'd always have 1 left over, so the number that was divisible by 4, 5, and 6 had to end in 0 or 5. And 4 would never have a number that ended in 5, so I knew it had to, the number that they all went into had to end in a 0, and the number that was found had to end in a 1.
Oh.
Does that make sense?
Yeah, yeah. I followed it that time.
So then I did the same thing, and I just went through all the multiples of 7 that ended in 1, and I subtracted 1 and made sure all of the 3 numbers were divisible by it.
Okay. Yeah, once you know it's going to end in 1, what does everybody see how we know that?
Yeah.
It's going to end in a 1 or a 6 because the 5 thing, but it can end in a 6 because the 4 thing, if you divide in 4, that means if there's going to be 1 left over, it's got to be odd. So it can only end in a 1. So then at that point, I would just start writing down all the multiples of 7 and look for one that ends in a 1. 7, 14, 20, 21. Maybe it's 21. And you just keep going, right? And every time you get to a 1, you check it. Now, what's the answer to this?
301.
301? Because the question that it asks is, how many tablecloths might have been? Are there other numbers that would work as well?
If you go higher, I bet.
Did anybody find any other ones? You're just saying that's the first one you came to. Okay. Who's got a problem that they wrote? This is number 6. That had something to do with the hot dog thing, or something to do with an original problem they think would, yeah. You want to?
Yeah, let me open it up. Mine was kind of just like the hot dog one. But what I did instead was I made up one with M&Ms and Skittles in bags.
Okay.
And, hold on, let me pull it up. And, I couldn't come up with something, so I said a girl needed to get exactly even amount of Skittles and M&Ms in bowls. So I think I said, let's see, I can't find it, but I think I said was there were 232 M&Ms in a bag. No, Skittles, 312 Skittles. So, sorry, one second. Almost there.
So there's so many things in a Skittle bag and so many things in an M&M bag.
Yeah.
You want to buy the number of bags, the correct number of bags of each, so you have the exact same number of each one.
Yeah.
Kind of thing.
And so I ended up having to find the least common denominator.
You mean multiple?
Sorry, yeah. Getting my words mixed up. And it turned out to be... Sorry.
If you think you've got a good problem number 6, and you want me to, in fact, let's just do this. if you think you've got a good one, email it to me and I'll choose the best one and put it on the exam. Your problem. So if you think you've got a good one that I would think would be good to put on the test, send it to me. Then you know for sure you're going to get at least one of the exam questions right? Just email it to me. Say, here's my problem number 6 that I think could be put on the test. Yeah.
It's just
Practice test? It's not open?
Oh, I didn't know that. For the exam?
Yes, when is the exam? It didn't show much. And like, I guess it showed something for Monday, but after that it was still October, so it didn't show me when anything was due.
Due next Monday, right?
What's due next Monday?
What? All the dates are so wrong. They're like October still.
I think that one's ready now.
Can't look at them.
And somebody was asking about which reflection set of questions. Well, now it's the only one available. Okay?
Wait, so where's the exam?
The exam is, it opens next Thursday and closes a week from Monday.
Is the personal resource, is that due Monday?
Personal resources also do Monday the 20th.
The 20th?
Yes.
Okay. I was like, wait.
Yes.